Okay, so let's talk about one more method of preparation from alcohols, and let me just write the reaction down very fast. It is ROH plus NaBr in the presence of sulfuric acid. Generally dilute, could be concentrated also, but it's just a waste of chemicals. To give me RBr, for example, plus NaHSO4 plus H2O, and it's pretty straightforward mechanism. If you look at it, you have H2SO4, you're going to protonate this, you get ROH2 plus. H2SO4 dissociates to give me H plus plus HSO4 minus, right? You have Br in solution, Br minus will attack, this will shift, and you got Na plus in solution, that will form NaHSO4, you get H2O, you get RBr, right? So that's basically the mechanism, super straightforward. Yet there are many snags which will face when you're doing this reaction, and I'm going to explain those snags to you. Step one, first one, you cannot prepare secondary or tertiary halides using this method. Why? Because if you remember, if I had something like this, for example, see whatever, right? And if I put this in H2SO4, actually, let's forget about, let's not make it dead, let's make it moderately concentrated, because I will tell you why in a minute. So moderately concentrated or super concentrated, doesn't matter. So anyways, H2SO4 concentrated. You know, H2SO4 is an amazing dehydrating agent, right? So now we use the box mechanism, because now we can just remove this, right? And remember, every bond, if it's not from the same, every bond if it's not from the same carbon contributes half a bond. Okay, what I mean by that is, I'm removing this bond and doing something with it. I'm removing this bond and doing something with it. Turns out what I do with this, I'll form half a bond here. With this bond, I'll form the remaining half bond here. So I'm going to get an alkene, right? So H2SO4, when it's a secondary or tertiary halide, secondary or tertiary alcohol will form a alkene. And you guys can know why also. I just do the box mechanism, but if you were secondary or tertiary, you would have gotten ROH2 plus, and then this will make it easier, because if it's a secondary or tertiary alkyl group, then R plus is highly stable. Once you get R plus in the presence of H2SO4, what will happen is the plus will, the carbocation will deprotonate. Okay, so I never told you guys what that means before, so I will tell you now. Consider this molecule. Okay, H. This is right. Yeah. So this is a carbocation, right? Now this guy can either get attacked by some nucleophile, that's one thing, but he can also do something else called deprotonation. So I can always write minus H plus, and then remember we can always write minus H plus, right? What will be the structural formula of this? I get 4 hydrogen and 2 carbons, so I get C2H4, and C2H4 is commonly known as ethene, right? You guys know this. So I get ethene. How does this happen? This hydrogen leaves as H plus. This hydrogen is removed as H plus. Okay, so this bond shifts here, thereby neutralizing the positive charge. Okay, so this is what we've been doing for so long, removal of H plus and shifting of bond. So, but generally what it is, you remove H plus and the bond falls on the atom itself like oxygen. In this case, it just shifts to neutralize this positive charge. Understand? So you can ask me, well, why don't I remove this H plus and plonk this bond on top of this guy? Well, that's because valency is not satisfied. Okay. So charge can be satisfied, which valency should also be satisfied, right? So that's another thing. Okay, so that's good. So that's basically what will happen. So this is what we call deprotonation of carbocations. So carbocations will deprotonate, C plus will deprotonate minus H plus to form alkene. Because you got that extra bond which is going to shift, which will shift onto an already existing bond here, so you get another bond. If you add a double bond, it shifts on to form a triple bond. Basically, that's the idea. Okay. So definitely you cannot form secondary or tertiary halides, because the carbocation will be nice, will be easily formed. Which easily formed is going to deprotonate. You can ask me, well, if carbocation is stable, then why does it deprotonate? I have told you this before also, carbocations are stable tertiary carbocations are stabler compared to secondary carbocations, stabler than primary. But that does not mean that carbocations are stable. Relatively, this is the stability order, but carbocations are highly unstable. There are very few carbocations which you can isolate. Okay, so mostly they're going to be always jumping around with our energy and trying to lose that energy somehow. Okay, so that's one of the arguments. So that's one thing you want to keep in mind. Secondary or tertiary halides cannot be prepared using this method. There's an exception to this also, which I will talk about soon. Another important thing is iodides is generally not prepared. Iodides aren't prepared. The reason for this is because iodine is notoriously known to be irritating. I minus can be oxidized to HI, which will start, which in the presence of H2SO4 will become iodine and so on. Okay, so I minus can become HI because of H2SO4's weirdness. You guys, I think you guys have heard of this reaction, right? H2SO4 plus some whatever Ki or something will give me K2SO4 plus HI plus something. It was there in your 10th grade textbook, I think. So, anyways, you get HI when you react any iodide with H2SO4, and iodide in H2SO4, HI with H2SO4 loves to do all kinds of nonsense like iodine will come proportionally to give iodine plus IO3 minus and all that stuff. So, it does a lot of funny things. I think I'm not. It will do a lot of funny things like this. Okay, don't quote me on IO3 minus, but generally, what will happen is this equilibrium will start playing. As you will see soon, this equilibrium plays a lot, okay, in different places. So, iodine has this property. Why does iodine have this property? Because iodine is see, H2SO4 is going to do what? It's going to oxidize you, right? It's an oxidizing agent. So, converting I minus to HI, what is the oxidation state here? It's minus 1. Oxidation state here is also minus 1. Okay, fine. Sorry about that. It's not going to oxidize in this step. It's going to keep you converting from Ki to HI. This step it will oxidize, right? The oxidation is minus 1, it's 0 here. So you're getting oxidized, right? H2SO4 loves to do that. But H2SO4 cannot do that on everybody because HBr and HCl do not face this problem of getting converted to bromine or iodine unless you have very high concentrations or whatever. Okay, the reason for this is because HI is a much stronger acid, so iodine is a much weaker base, and so you got a lot of other parallel things playing in the background. Okay, so but you just want to remember this HI becoming I2, this equilibrium will cause lots of problems for us even in the future. I will, in fact, maybe I'll make a video just on this guy, explaining why this happens in much more detail later. But for now, just take my word for it that HI becomes iodine, okay? Just so that we can move on. That's one more thing we test. Other than that, I just want to tell you one more fact. Remember, we said that we protonate for a reason, right? We consider this to be the reaction because then the electron, then this bond becomes super weak. We can consider it to be non-existent. That stuff. Another reason why we protonate is because nucleophiles have this hierarchy among them, right? We talked about strong nucleophiles, half strong nucleophiles, moderate nucleophiles, and all that stuff. And of them, OH minus is a better nucleophile than Br minus, Cl minus, I minus, everybody, right? And the ego issues here is that Br minus cannot replace OH minus because Br minus is a weaker nucleophile than OH minus. OH minus is not much. You say, I don't care if you take every electron away from me, you cannot take my honor away from me. So it's not going to leave until you do something about it. So, as you know that OH minus is much stronger nucleophile than H2O, right? How do you know this? Because NaOH is a much stronger base than water. So OH minus is a stronger base than water, which generally means that OH minus is a much stronger nucleophile than water. So if I can convert OH minus into water, which is this basically, right? That makes it a much weaker nucleophile compared to bromine or acetone and iodine. So water is somewhere down here. Because of which you can now remove it. Also because this becomes a nice molecule. Remember, nice molecules, they are good, they have no self-transference issues, so they can just walk away into solution. So it becomes a good leaving group also. So we do it for three reasons. One, to reduce nucleophile strength. Two, to make it a better leaving group. And three, to reduce the bond strength. Okay? So those are three points of theory which you want to keep in mind. And that, after all this hard work, finally completes preparation of alkanes from alcohols. We still have about 3 methods of preparation which I will skip through very fast. Okay, and then we will go to preparation of haloarenes, which also will be very simple and straightforward. After which we will go to chemical properties. Okay, that will take a little while, and then we will discuss a problem set. Okay, so take care. You should actually take a break now. Okay, see you.